Hope you're having a good day. I'm going to talk about some Raman imaging today. And this is taking pictures with spectroscopy. Believe it or not, you can do this. First off, start by imagining a molecule with a carbonyl bond. A carbonyl bond is just a carbon double bonded to an oxygen. And imagine these three molecules adsorbed to a metal surface. So this is our metal surface, and we have some molecules containing carbonyl bonds. The rest of the molecule we're not going to care about. Now imagine we take a laser and we point it at this sample because we want to take a Raman spectrum. Imagine we point our laser in different spots. The first spot might be way over here to the left. The second spot is a little closer to the center. Third spot's in the center. Fourth spot a little bit to the right. And then fifth spot all the way to the right. Sort of like the following. So our first spot that we're taking a Raman spectrum is this first dotted circle. Second one's the second dotted circle. So on and so forth. So in total, we collected 5 different Raman spectra. And yeah, so the dotted circle represents the focal point of the laser, and everything inside the focal point is going to give us a Raman signal. So if there's nothing inside the focal point, we're not going to get any Raman signal there. And where there is a lot of stuff, we're going to get a lot of Raman signal. So essentially, what we did was collect 5 different Raman spectra that look like the following. Okay, so we took 5 different Raman spectra at 5 different points in space, and we got 5 different Raman spectra that look like this. Now in point 1, there's no molecules of our interest, so we see no signal where the carbonyl band shows up. The carbonyl band shows up around 1700. Now in 2, there's one molecule with the carbonyl bond. So in some arbitrary units, our intensity of our carbonyl peak has an intensity 1. In spot size 3, we have 3 molecules. So the carbonyl peak is, in arbitrary units, 3. And then with 4, it's 1, and 5, it's 0 again. So what we essentially just did was map out where is our molecule on the surface of the metal. And we found where most of it is. Most of it is in spot size 3. So we can take the information in these 5 different spectra, and from each spectra we're going to collect 1 bit of information, and that bit of information is going to be the peak intensity at 1700 wave numbers. So for spectrum 1 it's 0, for spectrum 2 it's 1, for spectrum 3 it's 3, for spectrum 4 it's 1, for spectrum 5 it's 0. And each of those different bits of information we can sort of map onto a pixel. So if we have 5 different pixels, so our first intensity at 1700 was 0, our second was 1, our third was 3, our fourth was 1, and our fifth was 0. And each of these little squares can be sort of thought of as a pixel. And now, these numbers we can represent, instead of numbers, we can assign a sort of darkness level to each of these numbers. And by doing that, we can make a one-dimensional image of sorts. So it would look most dark at the center, like that, and then it would be a third as dark in the squares right next to the center, and then the squares next to those, it wouldn't be dark at all. So essentially, what we did by moving our focal spot in 5 different spots was we formed a one-dimensional image of where our molecule is on the surface of the metal. And the metal doesn't have a Raman signature, that's why we didn't see any other peaks. The only peak that was Raman active in our molecule was the CO peak, which showed up at 1700. So, I mean, we can call this image an image of the intensity at 1700 wave numbers. Now, we can generalize this technique and we can go up a different dimension. Imagine if we have molecules in the following pattern on the metal, but now we're thinking in 2 dimensions. So the dots in this square represent our molecules with the carbonyl bond, and just the background just represents the metal, and this is in 2 dimensions. So if we take our laser and we do the same thing we did in 1D, except we do it a lot more often, so we might have our mirror here at first, not our mirror, we might have our laser here at first, and then we move our laser over here, and then we move it over here, and we can do that many, many times, and once we reach the end, we move our laser over here, do it again, move up a row, do it again, and so on and so forth. And we can collect many, many spectra, and we do the same process we just did, and we might end up with something like the following. So, we might end up with something like this if we repeat what we just did, and in this case, we took 10 spectra on this row, then we moved our laser here, took 10 spectra, repeated that 10 more times. So in total, we collected 100 spectra, and each pixel here, within each pixel, is the amount of intensity that was at the 1700 wave number mode. And I really should have even shaded in these squares a little bit, because there might be some molecules around these molecules here, because it's not going to be perfectly sharp. But basically what this image tells us is how the molecules on the surface of the metal were formed. It tells us they were in the shape of a smiley face. So that's how Raman imaging can give us powerful information. It can tell us the spatial distribution of molecules on a substrate. And of course, I mean, there's details I'm ignoring, such as the resolution. For instance, you're not going to have a really high peak here and then move a little bit and then have 0 peak. You know, you're going to have a high peak on 1 pixel, and then you're going to move a little bit, and then the peak's going to go down a little bit. You're going to move the laser spot a little bit, and the peak's going to go down a little bit again. It's going to approach 0. So this, where it's dark here and 0 darkness there, is kind of, you know, I'm kind of ignoring these things like resolution. And I'm also ignoring the fact that we're imaging single molecules, and things such as noise. I'm not thinking about those. But I think you still get the point of how you can get an image from the way the molecules are distributed on the substrate. And now hold on a second, there's more I want to talk about. So in our case, we only had 1 molecule with a carbonyl bond, and we were essentially imaging where's all the carbonyl bonds on the metal? Now, what if we had 3 different molecules with 3 different modes? Say one of the molecules had a C double bond O, another molecule had a carbon double bond to carbon, and another molecule had a carbon triple bonded to nitrogen. So this is an O here. So this carbonyl mode is going to show up around 1700 wave numbers. This CC bond is going to show up, I actually don't even know, maybe around 1400. But that might be completely wrong. And the CN bond is going to show up, I also have no idea, maybe around 2200 wave numbers. But it doesn't matter where they show up. The point is that the peaks are distinct. So essentially, if we have 3 different molecules, and each of these molecules have their own unique vibrational mode, we can essentially, by taking the same 100 spectra, we can make 3 images. Because we can make one image of the intensity of the 1700 wave number mode, we can make another image of the 1400 wave number mode, we can make another image of the 2200 wave number mode. And in that way, Raman imaging gives us a lot more information than other imaging techniques such as fluorescence might do. And since we can make a specific image for each molecule or for each bond, we say Raman imaging has chemical specificity. And I think you know what that means. That means each image is specific to its own unique chemical or its own unique vibrational mode. And chemical specificity is one of the major advantages that Raman imaging has over other imaging techniques. So, I hope you understand how you can obtain an image or a picture by using Raman spectroscopy. I hope you enjoyed that. Thanks for watching and have a great day.